The human eye is a marvel of biological engineering. At the heart of this intricate system lies the pupillary mechanism. This system controls the size of our pupils, regulating the amount of light that enters our eyes. It's like having a built-in camera aperture that constantly adjusts to changing light conditions. This mechanism is vital for maintaining clear vision in various lighting situations. Without it, we'd struggle to adapt to different light levels, making everyday activities challenging. The pupillary mechanism is an involuntary process happening automatically. This automatic response protects our eyes from sudden changes in light intensity. Understanding the pupillary mechanism has practical applications in medicine, psychology, and technology. Doctors use pupil responses to assess brain function. Psychologists study pupil size to understand emotional reactions. And, in technology, pupil tracking is used in virtual reality systems and smartphones for security features. At the core of the pupillary mechanism are two key players: the iris and the pupil. The iris is the coloured part of our eye and a muscle that controls the size of the pupil. It's made up of two types of muscle fibres, circular and radial. These muscles adjust the pupil's size, much like the aperture in a camera lens. The pupil is the opening at the centre of the iris, allowing light to enter the eye. The size of this opening determines how much light gets in. When we say our pupils dilate or constrict, we're talking about the iris muscles changing the size of this opening. In bright light, the iris constricts, making the pupil smaller to reduce light entry. In dim light, the iris relaxes, allowing the pupil to dilate and let in more light. This constant adjustment happens without us even realizing it. Our pupils can change size in a fraction of a second. This rapid response is essential for protecting our eyes from sudden bright lights. The next time you look in a mirror, try shining a light towards your eye. You'll see your pupil shrink almost instantly. It's an incredibly responsive system. The pupillary mechanism is all about balance. It's a constant dance between dilation and constriction. Dilation is when the pupil gets bigger, allowing more light into the eye. This happens in low light conditions or when we're excited or interested in something. Constriction is when the pupil gets smaller, reducing the amount of light entering the eye. This occurs in bright light or when we're focusing on something close up. The process of dilation involves the radial muscles of the iris. When these muscles contract, they pull the iris outwards, making the pupil larger. Constriction involves the circular muscles of the iris. When they contract, they squeeze the pupil smaller. The speed and precision of this process is remarkable. Our pupils can change size in less than a second. This rapid response is crucial for protecting our eyes and maintaining clear vision. This constant adjustment allows us to see clearly in a wide range of lighting conditions. Behind the scenes of the pupillary mechanism is a complex network of nerves and signals. This network is part of the autonomic nervous system, which controls many involuntary functions. The autonomic nervous system is divided into the sympathetic and parasympathetic systems. The sympathetic system is responsible for pupil dilation, often associated with our fight or flight response. The parasympathetic system controls pupil constriction, active when we're relaxed or in bright light. These two systems work in a delicate balance, constantly adjusting our pupil size. The The signals from these systems travel along different nerve pathways to reach the eye. The sympathetic signals come via the long ciliary nerves, while the parasympathetic signals travel through the short ciliary nerves. This dual control allows for precise and rapid adjustments to pupil size. It's a testament to the incredible complexity and efficiency of our nervous system. The pupillary mechanism plays a crucial role in our everyday lives. Imagine you're reading a book in a dimly lit room. Your pupils dilate slightly to let in more light, helping you see the text more clearly. Now, picture yourself walking out of that dimly lit room into bright sunshine. Your pupils quickly constrict to protect your eyes from the sudden brightness. This rapid adjustment prevents you from being temporarily blinded by the change in light intensity. The pupillary mechanism also plays a role in our emotional responses. Pupil dilation can be triggered by emotional arousal or interest. It's one of the reasons why the phrase, "eyes are the window to the soul," holds some truth. Our pupils can reveal our emotional state, often without us being aware of it. When we make eye contact with someone, our pupils tend to dilate slightly. This is thought to be a sign of attention and engagement. It's fascinating to think that this tiny adjustment in our eyes can have such an impact on our social interactions. The pupillary light reflex is a fundamental aspect of the pupillary mechanism. It's the automatic response of the pupil to light intensity changes. Light stimulates photoreceptors in the retina. These send signals along the optic nerve to the brain. The protectal nucleus in the midbrain controls pupil size. Signals go to the Edinger-Westphal nucleus, controlling the parasympathetic response. This causes the pupil to constrict. The entire process takes less than a second. This rapid response protects our eyes from sudden light changes. The link between pupil size and emotional states is a fascinating area of study. Our pupils don't just respond to light, they also react to our thoughts, feelings, and decisions. Studies have shown that our pupils tend to dilate when we're emotionally aroused, regardless of whether that arousal is positive or negative. Pupil dilation is linked to the activation of the sympathetic nervous system, responsible for our fight or flight response. Pupil size can also indicate cognitive load. When we're faced with a difficult mental task, our pupils tend to dilate. The harder the task, the more the pupils dilate. The size of someone else's pupils can affect how we perceive them. People with larger pupils are often perceived as more attractive and more interested in social interactions. It's a reminder of the complex interplay between our physiology and our social behavior. The pupillary mechanism has significant medical applications. Doctors often use pupillary responses as a diagnostic tool. One common test is the pupillary light reflex test, which involves shining a light into each eye and observing how quickly and symmetrically the pupils constrict. Abnormalities in this reflex can indicate various neurological problems. The pupillary light reflex is also used to assess brain function in patients with head injuries or in comatose states. Pupil size and reactivity are important indicators in emergency situations. In cases of suspected drug overdose, pupil size can provide crucial information. In neurology, a condition called Horner's syndrome is diagnosed partly through pupillary observations. This syndrome, caused by damage to the sympathetic nervous system, results in a smaller pupil on the affected side. By carefully observing these pupillary differences, doctors can diagnose this condition and potentially identify the underlying cause. As our understanding of the pupillary mechanism grows, so do the potential applications. One exciting area of research is the use of pupil responses in lie detection. Some researchers are exploring whether pupil dilation could be a more reliable indicator of deception. Another promising field is the use of pupillary responses in the diagnosis and monitoring of mental health conditions. Some studies have found differences in pupillary responses between people with and without conditions like depression, anxiety, and PTSD. In technology, pupil tracking is becoming increasingly important. Virtual and augmented reality systems use pupil tracking to improve the realism of their displays. By knowing exactly where a user is looking, these systems can render the highest detail in that specific area. This not only improves the user experience, but also reduces the computational power needed. Some researchers are exploring the possibility of using pupillary responses as a form of communication for people with severe motor disabilities.